Thanks, everybody. Appreciate you all being here on the last day of the conference. My name's Scott. I'm an assistant professor at UCLA's Anderson School of Management. This is some joint work with my colleague Francisco, who unfortunately couldn't be here, although he may be watching from afar. So I'm really excited to tell you about this project, and it's motivated by charitable giving for nonprofits. So I just very briefly give you some intuition about how big this industry is in the US. And I say industry, we're talking hundreds of billions of dollars annually. And a lot of this does come from large scale donors, but a non-negligible percentage of it comes from these smaller scale donors, predominantly use online fundraising. So just to give you a sense of this, on one day, Giving Tuesday, which is the Tuesday before Thanksgiving, online fundraising totaled over $1 billion. So this is something where if we can improve giving, even by a couple of percentage points, this has a pretty profound impact for organizations that support. So today we're going to think about just one way of doing that. There's many, of course, that you can think about, but we're going to focus on the set of suggested donation amounts that are offered to donors on these fundraising pages. So I'm going to call this a default menu. And what I want to highlight here is that we have 3 art museums, 3 ostensibly similar institutions, and yet they have very different default menus that they're presenting. And this is, not just cherry-picked examples. This is pervasive across the space. I'll show you one more later. And what we want to think about is, okay, there's size of the menu, there's range, there's spacing, all of these different decisions that you can make. So with that in mind, we want to first think about, okay, are these default menus even effective? Is there a reason that so many institutions use them? And I promise the answer to this will be yes, and I'll get through it quickly because otherwise the talk is fairly meaningless. And then given that information, how can we use some amount of data to efficiently and optimally design these menus, right? It's a combinatorial space. It's going to be difficult to do this efficiently, but we're going to be able to do this using a nice connection to facility location. And then we're going to take a step back and think more strategically. If you're a nonprofit organization, should you invest in technology to personalize these menus? What's the value of doing something? Okay. If we have time at the end, I'll give you a little bit of data and a case study of how we can apply our framework. But for the most part, I'm going to focus on this optimization and personalization piece. Okay, so I promised very quickly some evidence for the effectiveness of defaults. This is true in a broad variety of contexts. It's true specifically in fundraising that defaults impact behavior. For fundraising in particular, though, the way that it impacts behavior does not necessarily translate to more revenue. You can think of these as magnets. And so you get some donors that are drawn upwards, but some donors that are also drawn downwards. So in a lot of these papers that I've mentioned, there's either negative or at least not statistically significant findings in terms of the revenue gains that are obtained from the menus that they show. Now, this could be because defaults just naturally can't generate revenue, or it could be that the limited number of menus that they're testing are not the right ones. Okay, so yeah, okay. With that in mind, let me give you a overview of how we think about this problem. I'll give you the framework that we're going to operate in, and then we'll think about optimizing within that framework. So in our model, we're going to have a single representative donor who's going to have some type theta, which is drawn from a known distribution G. And let me first describe how this donor behaves in the absence of defaults, in the absence of suggestions. So this theta determines the shape of the donor's utility function. We're going to make minimal assumptions on this. I'm going to say that it's strictly concave. We can, for the most part, relax this strict assumption. But this is nice for the purposes of the talk. It means we have a unique maximizing value T of theta. And so without any default suggestions, they'll donate T of theta. They'll enter that often in this other box that you see on these websites. However, if the nonprofit offers a default menu, say 5, 10, and 15, we're going to incorporate that into their utility in a fairly standard way. You're thinking about the literature on defaults by adding some constant epsilon, where the constant is drawn, it's specific to the donor. It's drawn from a known distribution F. We're going to call this their suggestibility parameter. It's how influenceable they are from these default suggestions. And what this means is that, okay, if their utility at their ideal donation is close enough to the utility that they get from one of these defaults, they'll pick default. This can lead to revenue increases. but it can also lead to revenue decreases. Or if their revenue at their ideal donation, their utility at their ideal donation is high enough relative to their utility at any of these defaults, they'll just stay where they are, which involves typing in some number into the box. Now, what does this epsilon represent? You can think of a number of different behavioral mechanisms. We're going to be agnostic to that, but you can think of a speedier transaction. You can think of some avoidance of a cognitive cost. All of those, you can think of as just this additive shock to their utility from clicking on this easy button. Yeah.
Are epsilon and theta independent?
Good. They don't need to be. I've written it this way, but yeah, they don't. Good. So the donor's problem is to pick the donation that maximizes their utility, and in turn, the nonprofit is going to choose a menu which maximizes their revenue change, the net gains that they get from this menu, where we're thinking about this in expectation over all donor types. So that expectation is with respect to the distribution of theta, and epsilon, which can be conditional. Any questions about this framework before I get into it?
Just to make sure I understand the behavior, this is a model through which every donor either pays the default or the closest, or either pays the optimal or the closest people.
You're ahead of me, I promise. Yeah, but yes. Okay, so, yeah.
The epsilons are independent of cost.
Good, so here we're assuming that epsilon is just one value for each of these defaults. That this is, both of your questions is something that we can relax. But
So I was thinking donation decisions being affected by what others want.
good,
And I think that's one of the things that's going on when you want suggestions. Maybe you understand from that others must be giving minimum of this, maximum of that. So it gives you an idea of the distribution.
yeah, we can capture some of that. Some of that's gonna be really hard, and offline I'll explain, yeah. Okay, so optimal design within this framework is actually gonna be pretty challenging. So here's the other example that I promised for you. There are 13 defaults here, including my favorite combination of $375 and $400, just in case you can't decide between those two. So the space of menus is large, is what I want to convey with this. So it's not going to be feasible to experiment or even enumerate over all of these combinatorially many menus. And so you need a simpler, a more efficient approach, and a good candidate is a greedy approach. And so here what I have in mind is sequentially and permanently adding the best next default to your menu until you reach some cardinality constraint or until you can't gain any more. This works quite well when your objective is monotone and submodular, but we have neither of those properties. I'll give you a brief example to motivate why this approach fails. So here we have two donor types, a low type and a high type. I promise I can find a utility function that gives me this behavior, but they're going to choose the closest default within $10 of their type. If I offer $30 in a menu, some of them will move up, the others will ignore it. If I offer 15, we actually get a net negative, so it's clearly not a monotone objective. If I add 30 to that menu, this is now better than just offering 15 separately added to what I get from 30 separately. So building on this intuition and devising a slightly more pathological example, we can show that greedily adding defaults can actually be arbitrarily suboptimal. So you give me any constant and I can show you that greedily adding defaults can be worse than that constant times the optimal menu's revenue change. So we need something else. And in fact, what we're going to be able to exploit is what Sohail previewed, which is there is a spatial structure to this problem. And in particular, if your ideal donation is between two consecutive defaults, you're going to do one of three things. You'll donate your ideal amount, you'll donate the amount below, or you'll donate the default above your ideal amount. What you won't do is skip a default and pick a higher one. And we think of this as some independence of irrelevant alternatives type of assumption. It follows from our base model. We can relax this, so I've emphasized base. We can relax this to some extent to capture a lot of well-motivated behaviors, but not all of them. And again, if you have questions, I can explain, or you can check out the paper for the categorization of which ones we can capture while still efficiently solving for the optimal.
It's also easily testable.
Yeah. Okay, so how are we going to use this property? Well, we can define value to go functions. And to calculate the value to go, we can start with some default kappa n. If we add a next default kappa n minus 1, the value to go is just the movement that occurs between the two, which doesn't depend on defaults outside of that range, plus the value to go from kappa n minus 1. Optimizing over that gives us the value to go starting at kappa n, and expanding this until we run out of defaults to add can give us a recursion that allows us to calculate the optimal set of defaults. If we have no cardinality constraint, you can do something similar, and things like that. Okay, so with that core of how you can optimize a default menu out of the way, let me now take that step back and think more strategically about, okay, how does that approach with distributional information compare to an approach with more information? To get at that, I'm going to consider 3 informational regimes. One where you have full information about a donor's type, one where you have partial information, you just know their generosity, and then a third where we return to this distributional setting. So the first case, I'll be quick on this. This is essentially first-degree price discrimination, where you know exactly how much they would be willing to increase their donation, and you offer that amount. We characterize this in the paper, but I won't spend any time other than to say we use this as our benchmark, and we compare these other 2 informational regimes against this full information. So this partial information setting we think is much more reasonable, and it corresponds to a world where you have historical donation information for someone. You know how much they've given in the past, but you don't know how suggestible they are. You don't know how willing they are to change how much they've given in the past based on your suggestions. And in fact, we can connect this very nicely to a posted pricing problem. I think this community is going to be very familiar with this. So the idea is that the distance between the default that you suggest and their ideal donation can be thought of as this price. And so if their type is large enough, if their suggestibility is large enough, you will get that price. So you want to set higher prices, higher defaults. But if their type is too low, they'll ignore your default suggestion and they'll give their just ideal donation amount. It's a 0 revenue change. And so we have this trade-off between setting a high price or getting a high probability of selecting the default. It takes a little work to connect this to the posted pricing setting because we're dealing with epsilon and not necessarily with the true value in terms of our benchmark. But we're able to show that for any fixed generosity parameter, if epsilon follows an MHR distribution, we can guarantee a 1/E fraction of our full information. And the key idea here is that we can get this constant performance ratio because all of our revenue changes are gains. We may not obtain, it might be 0 if the price is too high, but we're not going to lose revenue. We're not going to get this downward movement that you might get. Now, when we relax our informational setting once again, we now risk revenue losses. And to give you some insight as to when that occurs, we can think of easier instances where donors are relatively homogeneous and suggestible. And in that case, you can just set a default that's high, and you'll get generally some good revenue gains across the spectrum of donors. But when they're heterogeneous, it now becomes risky. If you want to get revenue gains from the low type donors, you often have to risk revenue losses from the high type donors. So to get at this intuition, we're going to parameterize instances based on the ratio of the support to our full information benchmark. And we can characterize how we do compared to our full information benchmark depending on this parameter. So if gamma is small, if it approaches 0, we can recover our partial information results. We can return to this 1/E constant factor performance guarantee. But as gamma gets large, all of a sudden we no longer have a constant factor performance. And if we have a small menu, this can be even worse. So these small menus can be costly. So the key takeaways here are segmentation is helpful. And in the absence of segmentation, large menus are helpful, which explains, at least to some extent, the large menus that you might see in practice. All right. So with a little bit of time left, I'm going to tell you about a case study. And so I want to emphasize, we think of this as an optimization framework. It can be helpful with a limited amount of experimentation, but some experimentation to fit this model of donor behavior is going to be necessary. We haven't done any of that, but we can leverage some other folks' experimentation to give us at least a flavor of what this would do. Now, it's a great experiment. It's a really nice paper by Altman et al. It doesn't give us quite the extent of experimentation that we would like to really calibrate our model, but we can make some assumptions and see what things. So I want to be clear, our counterfactual results here are not a claim that this is exactly what would happen, but it does give you a sense. So here there's 4 treatment groups. There's no default, and then there's 3 singleton default suggestions of 10 euro, 20 euro, and 50 euro. And in their paper, they found in 2 of those cases negative revenue gains, and in the third positive but statistically insignificant gains. So we use this information to construct an instance. I'm happy to go over the details offline if you want. I just want to briefly highlight our results, once using our base model and once using what we think is a slightly more realistic extended model. In both of those cases, we find that optimizing the default menu can lead to meaningful revenue gains, even though these experimental treatments didn't perform well, nor would our model predict that they'd perform well. So we think that there is potentially some value in using minimal experimental data to guide what you try next and speed up this process in this combinatorially large space of things. Okay, so wrapping up, what have we done? We have a dynamic programming formulation for solving the optimal set of defaults. We've also given some insight into the value of personalization. And in the paper, you can check out all of the generalizations and extensions that we can use to ideally incorporate whatever model of donor behavior you want while still having an efficient solution to this optimization problem. Going forward, I think one of the most interesting things is to think about how to take this optimization framework and combine it with experimentation to make that process seamless and efficient, quick, and hopefully implement something in the real world. So I'll stop there. Thanks, everybody.